Hello guys, you're welcome back to the AI in Civil Engineering course. Ever since we've begun the linear regression model, we have seen exactly what a linear regression model is. So in a linear regression model, what we're basically looking for, or what we're basically looking out for, is to get the parameters, the best value of the parameters that minimizes the loss function. Okay, and then we saw that, okay, to minimize the loss function, basically you can use the ordinary least square error method. And then in the ordinary least square error method, just a quick recap, this was the loss function. We say, okay, this was the loss function. Then we know that this loss function is dependent on beta naught and beta 1. And then to get the minimum value, we just did a partial derivative of this loss function with respect to beta naught, we equated to 0. We did the same thing for beta naught, and then we solved the equation analytically. Not me, generally. The equation will be solved analytically, and then you will arrive at this equation. This is the closed form equation that can be used for, every form of feature you have. But to make it simple, just for the case where we're working with just one feature, this equation could just be broken down into this, where our beta 1 is this formula and our beta naught is this formula. So this is an exact method. And what makes it an exact method? When something is an exact method, it means that there is only one formula, there is only one answer, there is just one global answer. You understand? So when you have a formula for something that says put your values into this formula and calculate it, it is an exact formula, okay? But for a gradient descent, we are still also trying to calculate the value for beta naught, and we're trying to calculate the value for beta 1 and beta naught, but we are not using an exact method. We are trying to use an optimization algorithm. So in this case, we will just, we will try to do something. If it doesn't work, fine, we'll update the parameter. We keep going until we arrive at the minimum position. So if you look at this diagram represents a gradient descent formula. I just picked this picture I picked it online. Okay, so these are the parameters. On the x-axis here, you have your theta naught. Theta naught is the same thing as beta naught. It's just some naming conventions, but they are totally the same. Okay. And then we have theta 1, which is the same thing as beta 1. They are the parameters. At this point in time, I would say that you should stop seeing theta naught as intercept and theta 1 as slope, because maybe at some point in time when you are at higher order, you have like 5 features, 7 features, it might start looking confusing. Hey, how many slope do you have? So don't see that slope and intercept. Maybe you should just start seeing it as just parameters. They're simply parameters, okay? But it's just an advice. It doesn't matter. Then we have the cost function. Well, the difference between a cost function and a loss function is that a loss function is only applicable to a single observation, and then a cost function is for the whole observations together. So it's a cost function, right? So now, say for example that you pick an arbitrary number of theta naught and an arbitrary number of theta 1, and then you put it in a cost function. Say, for example, that cost function is the same one, the same function, okay? Now, you will arrive at a particular value. You get a particular value on the y-axis. So the value could be here. And now, if you look at this position, you will see that this position is at the top of the graph. And this is like the maxima, okay? You're not trying to have a maximum cost function. What you're trying to have is the minimum cost function. Because in essence, what is a cost function? The cost function is just basically the function that expresses your measured value and your predicted value. So when the cost function is very small, it means your measured value and prediction and the predicted value, they are very similar. So it's more like a very good result. So you don't want high cost function. So you don't want to be at the top of this hill. You want to be at the bottom of this hill. So you could be here, you could be here, you could be here, you could be anywhere. So there are so many low positions on this hill, and for that we call them local minimum, okay? Local minimum. There is something called global minimum. Global minima is just the lowest point in that function in the whole domain, all right? And then local function is just like the lowest point in that area. There is no lowest point anywhere in that area, but it's not essentially the lowest point in the whole domain. Okay, so say for example you are here. Your final goal is to come to the bottom of the hill. So you want to come either here, or you want to come here, or you want to come to any low position on this function. So you might decide to come, maybe you go like this, you go like this, 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 until you arrive here. And if you took this direction, maybe you come like this, until you arrive here. Okay, so now the point now is, how do you move? So for an arbitrary value of theta naught and theta 1, when you put it in the cost function, if you are here, you will see that, okay, yeah, this is very high. Then you update the value of your theta naught and theta 1. When you update the value, you can come here. Also, you need to decide how you move. So do you just jump very high? Do you move fast, or do you move low? That concept itself is called learning rate. So how far you move. So you will see that there are different steps. You have 1, 2, 3, 4. So it's just like the distance of how much you move. That is called the learning rate. So you will see that this is like an iteration process. You first of all choose an arbitrary version of theta naught and theta 1. You put it in the cost function. You just arrive anywhere on this whole domain. And then when you put that back into your linear regression function, if you calculate your loss function again, and then you see this is very high, you still do another iteration. You take a step, you come down, you take a step, you come down, you keep going until you come to any local minimum. Or maybe you might be lucky to get to the global minimum. But then this is the twist. When you're working with a linear regression model, well, for a linear regression model, you don't have local minima. You only have a global minimum, which means there is only one minimum position. And this is exactly what explains a linear regression model. So this essentially is not a linear regression model. This is called a convex function. You have a convex function. It's like when you have this, but you turn it upside down. Okay. So initially you could be here on this position. Let me try to, maybe I've been using cursor. So let's say initially this is your beta naught. This value here is your beta naught. And then on this axis is your, that's beta 1 and beta naught, okay? And then in here is your cost function. You can call it L. So if the value of your beta 1 and beta naught makes you to be on, what color can I possibly use? Let's see, maybe this. So if the arbitrary value of your beta naught and the arbitrary value of your beta 1 and beta naught makes you to arrive here in the first step. So you agree with me that this position is the lowest position in that function. So you are trying to come here. So you can either come like this, come like this, come like this, come this way, come this way, this way, this way, this way. Or maybe you can come this way, this way, this way, this way, this way, this way. You can even come this way, here, 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 here. But no matter how you go, no matter how arbitrarily you go, you are still coming back to this position because this is the global function. So when you are working with a linear regression model, you have a convex function. Okay? For a linear regression model, the kind of function you have is convex. And this is how it means you only have a global minimum. Unlike here, you have local minimum. This position is a minimum, but it's not the local. This position here is a minimum. If you arrive here, you will say, yes, you are at the bottom of the hill, right? So it is a minimum, but it's not essentially the lowest. But as far as a cost function, as far as a linear regression model is concerned, you only have one global minimum. And that's exactly why when we were working with OLS, you remember, OLS just equated this to 0 and it gave us a formula. Why? Because it knows there is only one global minimum. So if there are so many solutions, you cannot have a formula. But because it knows that you only have one solution. That's why you have a formula, okay? So in a linear regression model, maybe it doesn't really make sense to use a gradient descent, okay? Because why? You know you have a global minimum. You can't really have so many, so maybe you don't need it. But I'm just teaching it so that maybe when we get to higher order, you will have, maybe understand it from whatever I've said here. Okay, so let's see, what are the process? How do you actually do this iteration? So for the gradient descent method, I am going to write my cost function. It's going to be the same cost function I've been doing. If you remember, in the last one, we used this cost function, which is L equals to summation of the measured value, measured target, minus the predicted target, and then we find the absolute, and then we simply squared it, okay? But then in this case, I'm going to add one more thing, which will be 1 over 1 over n. The n simply means that I am taking the mean, okay? So I'm doing the mean. I'm not simply just summing everything up. I'm also taking the mean. But then there is this very common concept that people do in machine learning. They add 2 here, just to tell you that, well, if you are trying to minimize the whole function, you can simply do for 2 number, like half of it. Okay, so it's still practically the same thing. It doesn't change anything. Whether you put 2 there or you don't put 2 there, it's still the same thing. So just like we did earlier, I'm going to replace this y bar. I can simply just maybe replace this. Remember that your y bar is simply your beta naught plus beta 1 x, right? So I'm just simply going to replace that. So I will say my loss function equals to 1 over 2n, then summation, and then I'll have this. I'll say y minus, I can have a bracket to bring this in. So I have beta naught plus beta 1 x, right? Then I square everything, I put square in there. Okay, so the first step that you do is that you also have to do a partial derivative, right? So you do the same thing. You do the L, then the beta 1. Well, the only difference in here that for OLS, when you do the L, the beta 1, you simply equate to 0. In here, we are not equating to 0. We will actually solve the equation. We will not just equate it to 0, okay? So if we do the partial derivative of this, which means that I'm trying to differentiate this equation with respect to b1, okay? So if this is a constant, we will simply have 1 over 2n, then summation. Then this 2 comes in here. Maybe I just simply multiply it here, times 2, it comes up. Then I have all of this back. I repeat it. I do y minus beta naught plus beta 1 x, and then you multiply by the differentiation of what you have in here. So if you differentiate the y, the beta naught is 0, because this does not have the variable we're looking for. So this will be 0, this will be 0, then this will be 1 times x. That will be x, then with this minus, that will be multiplied by minus x. All right, so at this point, 2, we cancel 2. I believe you agree with me. So this equation will simply become 1 over n, 1, or maybe I should just write it downward. So this equation of the L, the beta 1, will simply become 1 over n. Then you carry back the summation. Then you have this. You have y minus, well, don't forget that the whole of this beta naught plus beta 1x is still the same thing as y bar, right? So I'll say y bar, okay, then everything multiplied by minus x. But I don't want to have this minus x, so I can simply rewrite this equation and say the L, the beta 1 equals to 1 over n, then summation. So now if I switch this, that will take care of the minus, right? Because this will now become minus y plus y bar. So I can do y predicted minus y, then everything multiply by x. So in here, we already have the equation. This is the equation for the beta one. Don't forget this equation because we are simply going to code it up. So you need to, so I would say this is equation, maybe equation 1 for this. And then if we do the same thing for, let me simply just copy this in order to save time. I'm gonna copy this whole thing like this. No. I'm trying to save time, but maybe in the process, I'm even wasting time. Control V. Can I change the color? Yeah, pen property. I want this to be something purple. Yeah, good. Yeah, this is nice. Yeah. Yeah, good. So now I've just simply copied that equation. I decided to save myself time. So this is the same equation. The first thing we did was to, we did the L, the beta one. So we are going to do the same thing, but in this case, it will be the L, the beta naught. So we do the L, the beta naught. So we will do the same thing. 2 here, differentiation. This is a partial differentiation. I hope you still remember partial differentiation. But if you don't, just look at the final answer, it's okay. So in here, you still have 1 over 2n multiplied by this 2 when it comes down, right? Then I carry the summation. Some people don't like carrying the summation, but I don't care. It's not going to be a problem for me. So I have y minus the same thing, beta naught plus beta 1x. And then I multiply this by, now differentiate this with respect to beta naught, 0. And then when you do this, you have 1. Okay, fine, good. You have 1, but there is a negative here again. So you simply have just minus 1. Good. Then when you do all of this, it is 0. Okay, then we arrive at the similar equation, but not the same. You have the L, the beta naught equals to 2. We cancel 2, so you have 1 over n. Then summation, you have y minus, instead of calling all of this, I can simply just say y prime, but because of this negative, this will still switch. So this should be the predicted and this should be the measured value. So this will become the formula here. If you look at this equation, which is something I will call equation 2. Well, equation 1 here and equation 2, they look the same, only that equation 1 has something here which is x. This doesn't have, so it's something like that. Okay, now good. So now that we have the partial derivative equation, what is the next step? Well, the formula is that we are trying to iterate. We are going to update the parameter each time. So the new formula. So say for example. Sorry, let's go back up. So say, for example, you were here. The first thing you do is you choose an arbitrary value of beta naught and beta 1. So let's say initially you were here. Now, for you to come to this new position, what do you need to do? You need to choose another value of beta 1 and beta naught. So how do you choose? That's exactly what we are trying to do here. So you are going to have a new value of beta 1 and beta naught. So every single time you do an iteration, every single time you move, the value of your beta naught and beta 1 will keep changing. It will keep changing. But the algorithm as to how they change is what I'm about to write right now. Okay, so it's like an equation. So you will say the new value for your beta naught is simply given as the, let me say, b new equals to b old minus learning rate. We call it alpha. This is not written properly. Call it alpha. Then multiply by what? Multiply by the L, the beta. Let me see, this is beta 1, then beta 1. Okay, then the same thing for the beta naught. So the new beta naught will simply be the old value of the beta naught. Old is spelled OLD. Old value of the beta naught minus learning rate multiplied by the L, the beta naught, right? So we already know the value of the L, the beta 1. This is it. This is the value. This is the equation. So this is the equation of the L, the beta naught. So you simply just need to bring in whatever you get in here. You just plug it here. Then alpha is learning rate. It's an hyperparameter. You have to decide if you want to use 0.1, 0.01, 0.001. And as I mentioned to you here, that learning rate is just like the step, how you take the step, that you want to take a sharp step. Because you see that maybe the steps are closely packed. One was here, the next one was here, the next one was here, the next one was here. How about if you just take the first step here and the next step is here? The next step could be here. You know, here you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 because, you know, you're taking small step. You could just have maybe 3, 1, 2, 3, and you come very fast, you know. So if you have a high learning rate, you will simply quickly get here. But if you have a small, it will take you time to get here. But why people don't use big value of the learning rate is because you might actually jump. You know, instead of you to come here, maybe you can just jump to somewhere else. So you never just converge, and you need to converge. Say, for example, you are in here. So you take one step, come here. Instead of you to come to this position, maybe because of that big step, you have jumped to this position. So before you know it, you are jumping up, jumping down, jumping down. You never actually go down to the last position. So it's better to take small step, okay? And then the BOD is just, the last value of the B you have. So if you just plug this in here, then you can get this. So this is all about gradient descent. So what we are simply doing in gradient descent is that it's an algorithm. We don't have a definite formula. We don't say this is the formula, code it up. What we just have is that, okay, look for the partial derivative, multiply it with the learning rate, and then subtract the last one in there. Then you keep going on and on. So if this value here gives us the minimum cost function, we can stop. If it doesn't give us, we put it in the linear regression model, we calculate the cost function. If the cost function is not minimized, we do this step again. We keep doing it again until we have a minimized cost function. So it's an iterative process. You keep going, and going. But for ordinary least square method, it's not an iterative process. It just gives you the formula and then you're done. So ordinary least square method is quite very fast and easy, whereas this is not so fast. But this is better when you have large data sets, okay? So in order not to waste time, let's just see how we can quickly code this up. So what you need to hold is you need to remember this equation 1. You need to remember this equation 2. Let me call this one. Let me call this one equation 3. And then I can call this one equation 4. So when we want to code it up, you will certainly need these 4 equations, which is equation 1, that is the L, the beta 1. You need to remember this as well. You need to remember this as well. You need to remember this as well. And that's all. Then we'll code this up. No library, no machine learning library. So let's see how we do that in the next video.